Question 12 is showing us this pattern where 1 is the first odd number, and if we take 1 times 1, we get 1, which is the first triangle number. And we can keep on going with the second odd number, third odd number, fourth and fifth, and this pattern keeps going. So the question is asking us to explain why this pattern continues as you go through the odd numbers. So the first thing we want to do is express an odd number, any odd number. We're going to take, we know that the nth odd number can be expressed as 2n minus 1. And so we can try this out, make sure it works. If we take our second odd number, our n is equal to 2. So we're going to have 2 times 2 minus 1, which is going to give us 4 minus 1, which is 3. And yes, indeed, 3 is our second odd number. So this expression works for any odd number. So what we want to do, we can see that in our pattern, what we're doing is we're taking whatever that odd number is, which is 2n minus 1, that's our odd number, and we're multiplying it by n, which is kind of the order that the number is in. So with this second example, it's our second odd number, so n is equal to 2, and we're multiplying it by what the second odd number is, which we've already shown here is 3. And so that gives us 6. In the pattern, we're saying that 6 is the third triangle number. And so we're going to express our triangle number as t to the 3 in this case, because it's the third triangle number. So, so our expression for the nth triangle number can be given as t to the small n. I'm using a small n here because this is different than the n, uppercase n I've used earlier. And our nth triangle number can be given by n times n plus 1 over 2. And so what our pattern is telling us is that this small n for our nth triangle number is always going to be equal to this expression here, 2n minus 1. Because we can see when 2n minus 1 was equal to 3, in this case, we got our small n as 3 here for our third triangle number. So we want to show that this is true, that small n is equal to 2 times big N minus 1. And so to do this, I'm going to substitute this expression 2n minus 1 in for lowercase n in this expression and see if it works out. So I have, in this case, 2n minus 1 times 2n minus 1 for our n, but we have this plus 1 here, so we're going to add 1, and this is all over 2. So if we work this out a little bit, we have 2n minus 1. This minus 1 and plus 1 just cancel out, and we get 2n here. This is all divided by 2. You can see we're multiplying by 2 on the top and dividing by 2. So these 2's cancel out, and what we're left with is n times 2n minus 1. And if we remember, that is our original expression up here. So we've shown that this pattern will always be true.